One of the uses for matrices is that it can be used to solve systems of equations. Recall that a matrix is a rectangular array of real numbers, and we like to talk about its order, its dimensions. This particular matrix has 2 rows by 3 columns, so we call it a 2 by 3 matrix. And if a matrix has the same number of rows as columns, we call that a square matrix. So this is a 3 by 3 square matrix. To find the order of matrices, we simply count the number of rows by columns. 2 rows by 2 columns, 1 row by 1 column, 3 rows by 2 columns, and 3 rows by 1 column. So when we want to use matrices to solve a system of equations, we start by writing an augmented matrix for that system of linear equations. So we start by writing the coefficients in this matrix. It will end up being a 3 row by 4 column matrix with the coefficients listed first, -1, 1, -4, and 3. And then we symbolize the equal sign with 3 dots and a 5, which is the answer to this equation in standard form. Then -1, 3, -1, with a -3. And finally 2, when we are missing the y, we hold its place with a 0, a -4, and then finally 6. That's an augmented matrix for a system of equations. So just as we did synthetic division when we were working with polynomials, for example, a 2x squared minus 6x plus 5 divided by an x plus 1, we would strip the variables off and write the 2, -6, and 5, and then put a -1 out in front. Same idea here. We're basically eliminating some of the writing, making it less tedious, and giving us another way to solve a system of equations. So in order to do this, we use something called elementary row operations. And there are 2 gentlemen by the name of Gauss and Jordan who were attributed to solving systems of equations in this way, so we call this also Gauss-Jordan elimination. So we determined that it was possible to interchange 2 rows if we need to. That's one of the elementary row operations. And we can also replace a row by a non-zero multiple of itself. So as long as we're not multiplying by 0 and zeroing everything out, we can replace a row by a non-zero multiple so that we can add it to another row to get some zeros and ones in our matrix. So for example, if I were trying to solve an equation where I had a 3x minus 4y equals 7, and a 1x minus y equals 3, we could eliminate the x by multiplying this whole left side by -3 and the right side by -3. So that's the idea here. First we're going to swap these rows and put the 1, -1, and 3 on the top row, and 3, -4, and 7 below it. And then we're going to multiply -3 times this whole row and then add it to the third row. So a -3 times 1 would be a -3. A -3 times a -1 is a +3, and a -3 times a -3 is a -9. So it's not a bad idea to do some pencil marks above so that you're not multiplying and then trying to add, multiply, add, the Henry Ford type of thing. So we're first figuring out what those values are and then adding them up. So that 3 and that -3 becomes a 0. The -4 and the 3 is a -1, and 7 and -9 is a -2. From there, we could use the same process to change the signs or multiply the second row by a -1, because if I add 0 to 1, I'll remain a 1, but if I add a +1 to a -1, I would get a 0, and a +2 with a +3 would give us a 5. And we can divide the second row by a -1 and get 0, +1, and +2. And that tells us what our answers to this particular system of equations would have been. Because 1x plus 0y is 5, and 0x plus 1y equals 2. So over here, we have this augmented matrix from above, and we're going to start by getting a 0 in this position. And we do that by adding row 1 to row 2 and putting it into the result into row 2. So 1 and -1 is 0. -4 and 3 is a -1. 3 and -1 is a 2. And 5 and -3 is a 2. So we still have our 0, -1, 2, and 2, but we could eliminate this 2 in the third row by multiplying the top row by a -2 and adding it to the third row. So the top row times a -2 would get us -2, +8, -6, and a -10. And when we add that to the bottom row, we would have a 0, an 8, because 8 plus 0 is 8. -6 and -4 is a -10, and -10 and a +6 is a -4. Now, why would we want to do that? Well, this particular matrix is in row echelon form. But the one below it is in reduced row echelon form. So what is the difference? Well, if we look at the reduced row echelon form, 0x plus 0y plus 1z equals 2. We can see that 2 is the value of z. 0x plus 1y plus 0z equals 2, so y is also 2, but 1x is equal to 7. So we can see the solution to this particular system of equations by simply looking at it when it's in reduced row echelon form. How is it different from the row echelon form? Well, it still has this downward diagonal of 1s, but instead of all of the other coefficients being zeros, the bottom 3 are zeros, and we have some others that are not. So if it's in row echelon form, you have the ability to do something called back substitution. And when you back substitute, you start by saying, okay, I know what z is. Z is 2. And so I could plug 2 in for z and use my next row above, the middle row, to say 0x plus 1y minus 2 times z is equal to -2 and solve from there. And once we have z and y, we can substitute them back into the top row. 1x minus 4 times whatever y is, plus 3 times the z, which is 2, is equal to 5. So it is a way to solve the system of equations with a combination of matrices plus the substitution that we have used before. What I'd like you to do is practice trying to get everything into reduced row echelon form. And if you run into a time constraint on a test or a quiz, then you could do the back substitution if you get it into row echelon form. But always practice getting it to reduced row echelon form on your assignments so that you get better at it and are faster. So we're going to solve this system using matrices. And we do that once again by writing the augmented matrix first. So if we have 3 as the coefficient for x, and -2 for y, 1 for z, and 15 for our constant, and a -1, a +1, 2, and -10 for our second row, and 1, -1, -4, and 14 for our third row, The strategy that I like to give to students is to always start by creating this column that has a 1 in the top row and 2 zeros below it. Because once we get a 1 and 2 zeros, that's going to help us be able to start then eliminating and getting it into a row echelon form. So anytime that we are multiplying something, another row, by something to eliminate a value somewhere else, that 0 is not going to impact anything. It's not going to add value to anything. So we want to try to get, very first of all, this 1, 0, 0 as the first column. Okay, so to do that, we're going to start by switching some rows around. We'd like this third row to be our top row. So we're taking row 3 and placing it into row 1. So 1, -1, -4, and 14 is now our top row. And hopefully you notice that if we add row 2 and row 3, we're going to eliminate the -1 and 1, that will become a 0, and also the 1 and -1 will also become a 0. So we will end up with 2 zeros. We would like to have those 2 zeros in this bottom row. So let's add row 2 plus row 3 and place them in the bottom row. So -1 and 1 is 0, 1 and -1 is 0, 2 and -4 is -2, and 14 minus 10 is a +4. And we have not yet done anything with the top row that was 3, -2, 1, and 15, so we'll place that into row 2. Okay, so things are looking better because we now have a bottom row that is really close to being solved. We'd love for it to be in the form 0, 0, 1, and that reveals our number z. So if we said that this was -2z equals 4 and we were trying to solve that, we would simply divide by a -2 to find out what z is. So we'll do the same thing in our matrix form. So we start by multiplying the bottom row by a -1/2 or dividing the bottom row by 2. -2. So 0, 0, 1, and -2 becomes our bottom row, and it's perfect. We don't need to do anything else to it. We're going to keep it the same. To keep things simple, we'll keep the top row the same as well. Try not to do too many steps in one turn. But let's take a moment to figure out how we're going to eliminate this 3. So if we take our top row times a -3 and add it to our second row, that's one of our legal elementary row operations. So a -3, +3, +12, and -42 is going to be added to, this is -3 times row 1, added to row 2. So -3 and 3 is 0, which is one of our goals, to try to get that column of 1, 0, 0. 3 and -2 is 1. 12 and 1 is 13. And -42 and 15 is -27. All right, so we have this column of 1, 0, 0, which is what we were hoping for. The next step is to try to get, and we also have our bottom row. Bottom row is figured out. So the next step is going to be to try to figure out how we can leverage this one to eliminate that one. So notice that if I add the second row to the first row, it doesn't change that leading one, but it will give us a 0 in this spot. So row 1 plus row 2, going back in row 1's row, 1 plus 0 is 1, negative 1 plus 1 is 0, negative 4 plus 13 is a positive 9, and negative 27 plus 14 is a negative 13. Bottom row is pristine, we keep it, we don't want to change that whatsoever. And then we're going to keep the middle row for the moment, or actually might be just as easy to say, let's make this middle row, multiply it by a negative 13. 0, 0, 1 times negative 13 is a negative 13, and negative 2 times negative 13 is a positive 26. Because if I add a negative 13 and a positive 13, we will get a 0 in that position. So negative 13 times row 3 going added to row 2, going into row 2. 0 plus 0 is 0. 1 and 0 is 1. Negative 13 and positive 13 is a 0. And negative 27 and 26 is a negative 1. So we are almost finished. We have our first column, that's 1, 0, 0. We have our main diagonal of all ones, and we have zeros in the other positions. The only thing we need to work with now is this 9. So to eliminate the 9, we can take the negative 1 in the third row, the whole third row, times the negative 9, and add it to the positive, to the first row. So negative 9 times row 3 added to row 1 is going to get us a 0, 0, negative 9, and a positive 18 added to our top row. 1 plus 0 is 1, 0 plus 0 is 0, 9 and negative 9 is 0, and a negative 13 and 18 is a 5. So if you're careful and you take your time and you watch your work and don't recopy something incorrectly or mess up with signs, you should have a good result. So now we know that our system of equation was solved, and x was 5, y is negative 1, and z is negative 2.